You know that little shock you get when you touch a doorknob? Or the flash of lightning in a storm? Or even just the fact that your phone can hold a charge? Well, that's all electrostatics, an invisible force that's shaping our world all the time. Today, we're going to pull back the curtain and see exactly how it all works. Let's get into it. Believe it or not, these two things are connected by the exact same fundamental property of matter. It's not magic, it's physics. And by the end of this, you'll understand the invisible threads that tie it all together. So here's our roadmap. We're going to start with the absolute basics, the spark of everything, and then get into the rules of how these things interact. From there, we'll see how to calculate the forces, how to visualize them, and finally, we'll talk about the energy they store. All right, let's dive right in. Before we can talk about lightning or circuits, we need to meet the absolute star of the show, the electric charge. Think about it like this. Mass is a property that causes gravity, right? Well, electric charge is a property that causes the electrostatic force. It's not something a particle has, like a little backpack. It's just part of what it is. It is woven right into the fabric of matter itself. Okay, so now that we've met our main character, let's check out the simple and totally unbreakable rules of the game. How does charge behave? The first rule is all about duality. Charge comes in two flavors. You've got positive, which is carried by protons, and negative, carried by electrons. And the rule is one you've probably heard before. Opposites attract and likes repel. So a positive charge will push other positives away, but pull any negatives closer. Simple as that. And then you've got these two big laws. First, conservation of charge. This just means you can't create charge out of thin air. When you rub a balloon on your hair, you're not making new charge, you're just moving it from your hair to the balloon. Second, quantization. This one's a bit of a mind bender. It means charge isn't some smooth, continuous fluid. It comes in tiny, individual packets. You can have one of these packets, or two, or a million, but you can never, ever have 1.5. So, just how small is one of these basic packets? Oh, it's tiny. I mean, ridiculously tiny. This number here is the amount of charge on a single electron or proton. It's so small, it's hard to even imagine. But, and this is the key, when you get trillions upon trillions of them moving together, you get forces powerful enough to create a bolt of lightning. So we know charges push and pull on each other, but how hard? I mean, can we calculate it? Well, yeah. Back in the 18th century, a physicist named Charles Coulomb figured out a way to do it with incredible precision. Now, before we see the whole formula, the logic behind it is actually pretty intuitive. First, pretty obvious, the more charge you have, the stronger the force. Makes sense. But second, the force gets weaker the farther apart the charges are. And here's the cool part. It's not a simple drop-off. If you double the distance, the force gets 4 times weaker. This is called an inverse square law, and it's one of the universe's favorite rules. It shows up everywhere, from gravity to light. And this diagram shows it all perfectly. You've got two charges, we'll call them Q1 and Q2, and they're separated by some distance. Coulomb's law gives us the exact mathematical tool to figure out the force between them, whether it's a push or a pull. This equation is pretty much the foundation for all of electrostatics. Okay, so calculating the force is powerful stuff, but it still leaves a big question. How does one charge know that another charge is even there to be pushed or pulled? The answer is an amazing concept called the electric field. So here's the mind-blowing idea. A charge doesn't really act on another charge across empty space. Instead, what it does is it changes the very fabric of the space around it. It creates this invisible field of influence. Then, if any other charge wanders into that space, it feels a force from the field itself. And to help us see this invisible field, we draw these imaginary lines of force. The rule is easy. The lines always show the direction a positive charge would get pushed, so they point away from positive charges and straight towards negative charges. And see where the lines are bunched up close together? That's where the field is the strongest. And this is where it gets beautiful. Look what happens when you bring a positive and a negative charge near each other. Their individual fields combine. The lines of force flow gracefully out of the positive and into the negative, creating this perfect visual map of the attraction between them. You can literally see the force. So we have these amazing maps of the force fields. But how can we measure the amount of field that's passing through a certain area? I mean, how do we count the lines? For that, we need a new idea called flux. Let's use an analogy to make this super simple. Forget electricity for a second and just picture wind blowing through an open window. The amount of air that flows in, the air flux, depends on a few things, right? How fast the wind is, how big the window is, and whether the wind is blowing straight in or at an angle. Now, let's just swap out the air for our electric field. It's the exact same logic. Electric flux is just a measure of how many electric field lines are poking through a certain area. The more lines that go through and the more straight on they are, the higher the flux. That's all it is. And this idea of flux leads us to one of the most elegant and powerful shortcuts in all of physics, Gauss's law. It's almost like a magic trick. It says that if you draw an imaginary bubble around some charges, the total amount of flux flowing out of that bubble depends only on the total charge you trapped inside it. Any charges outside the bubble, they don't matter at all. It's an incredible simplification. We've talked about charge, we've talked about force, and we've talked about fields. There's just one last piece to this whole electrostatic puzzle: energy. Turns out, every electric field is a storehouse of potential energy. The best way to think about this is to picture a big hill. You know it takes work. It takes energy to push a boulder up that hill. And at the top, that boulder has stored potential energy. Electric potential is the exact same idea, just with charges instead of boulders. It's a measure of how much work it takes to push a charge to a certain spot in an electric field. And the sign of that energy tells a story. If you're pushing two positive charges together, which naturally want to fly apart, you have to do work. You're fighting the field. The system stores that work as positive potential energy. But with a positive and a negative charge, they want to come together. The field does the work for you, pulling them in. In that case, the system actually stores negative potential energy. So, okay, that was a lot of physics. Why does any of it matter? Well, it's literally all around you. The precise forces from Coulomb's law are how photocopiers and laser printers work. The ability of electric fields to store energy, that's what a capacitor does in basically every electronic device you own. And that last idea, electric potential, we have a much more common name for it: voltage. It's the push that drives the current through every single circuit. So when you think about it, everything from a balloon sticking to a wall to the most complex computer chip comes down to these same few fundamental rules of charge, field, and potential. It really makes you wonder, doesn't it? If we can understand so much from just these principles, what else is waiting to be uncovered just by looking at the basic instructions the universe is running on?